The main motivation behind this is, so this is the one thought that I had, right? So all of us, so we have only used computers all this while. So why not build one, right? Because any day making something is cooler than using it. Like whatever you take, right? You take music, like you listen to music, you consume a lot of music, but then if you make music yourself, the feeling is much like more satisfying, right? So here's what I'm going to tell you. I'm going to tell you that you can do it in 3 days flat. So that is going to be the main motivation behind this workshop. So in 3 days, we are going to give you a computer in your hands. All right. So here's how we're going to do it. On the first day, that is today, we'll go over the fundamentals. So whatever I had just announced before, then we'll dive into the simplest possible one architecture. So it's like basically you can consider it like a block diagram, and then we'll tackle one block at a time, build one block at a time, and then finally all we have to do is put it all together and it will just work. Okay, so is that clear? So how many of you are waiting, can't wait to start? So before we begin, I guess, how many of you have heard of simplest possible computers? So anywhere. So have you ever come across the term anywhere, let's say somewhere on the internet, or like you're reading some book and it popped up? So any of you familiar with the term simplest possible computers? So yeah, if you don't know, no worries. That's what we're here for. And if you do, it'll be a nice refresher. So in a nutshell, right? So the simplest possible one computer uses 8 bits for everything. All right. So it deals with 8-bit numbers. It deals with, so everything, all the registers and whatnot. So all the components are using 8 bits at a time. Okay. So the instructions are 8 bits and all of that. So that's 8 bits. So remember that 8 bits. And it is called simple as possible, right? So the only thing that this computer is going to be able to do is addition and subtraction. But hey, we're going to build a computer anyways. So this brings it down all the way to the bare bones, the simplest possible. So remember it, you will be able to perform addition and subtraction using this computer. And finally, so this is a bit of a technical term, which we will be addressing later today. So remember that it follows the von Neumann architecture. So it is a way of designing a computer. So we will be addressing what von Neumann is and all later today. So just keep these 3 things in mind as we progress through this workshop. So now I'll just hand it off to Skanda to start things off for today.
So hello everyone, a very good evening to all of you. I'm pretty sure you're all extremely excited to build the SAP1 computer. So let's begin. I'll just share my screen. Give me a second. And we are good to go. So firstly, well, yes, this computer, the SAP1, is more of a computer architecture thing, but that does not mean we should not touch at the basics. So we'll have a quick recap of number systems and a few more things, such as combinational logic, flip-flops, etc., registers, so that we get a feel for it and it's fresh on our mind, so that we can carry on it to the computer architecture part and then building the computer. So let us begin. Again, a questionnaire. Let's keep this session a very interactive one. How many number systems are you acquainted with? How many do you know? How many have you heard of? Just put it in the chat box. Let's see. Any answers? Binary, or one of them I told. Any more have you heard of? Number systems, decimal, hexadecimal. Very good. Yeah, exactly. Exactly the things I was looking for. Great. Okay. So yeah, first we'll be looking at the binary number system. Binary itself suggests that the whole number system comprises of only 2 numbers, that is 0 and 1, as you very well know. So that is what we have. The left picture is, let's say, an example of a bit stream, because 0 or 1 is called as a bit, right? So it is a bit stream. And on the right, we have the most important thing. You can see it on your TV remotes, etc. A circle and a small line, right? On and off. Those are the only two things which our computer will understand. You will hear many teachers at many places or many videos where they say, computer just understands the binary logic, that is 0 and 1. But today we will see how exactly and why exactly it understands only that much and nothing else. Okay, so 0 and 1 is analogous to off and on, true or false, yes or no, such kind of questions. Okay, so 0 specifically usually means low voltage, and 1 is analogous to high voltage. Computer understands the power surges given to it as voltages. So that is what we'll see today, not at the electronic level, but on a slightly higher level, at the machine level. Okay. So this was about binary systems. Next, we'll touch down upon the hexadecimal number system. Okay. The hexadecimal number system, as the name suggests, it is hexa and decimal. Decimal is 10 and hexa is 6. So totally there are 16 numbers in the whole number system. Okay. So what are those numbers? Let us look at those. It varies from 0 to F, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the single digit numbers. And then for all the double digit numbers, we have until 15, that is A, B, C, D, E, and F. So their binary and decimal equivalents are given such as it. You can just have a look at it. I'm quite sure all of you already know that. So that is the basics of hexadecimal number system. You would have all done it in your computer classes, conversions between them, between octal and this, even decimal points, etc. We'll not be touching on those things. We just are here to this will be useful when we are using instructions. We give instructions in hexadecimal. That is what computer understands. It will convert by itself into binary using instruction decoder, etc., and then it will perform the operation. So these are the things which we need to know before we go into those topics. Next, let us see, this is another very important aspect which we are going to use. Basically, it is used for subtraction. I'll show it to you later. So 2's complement. So 2's complement is something used to represent a negative number in binary. So we just can't put a minus sign and a bit stream, right? Because computer won't understand that minus sign. How does it understand there is a minus? So you need to tell it in some way, right? So 0, if let's say we are dealing with sign numbers, sign binary numbers, 0 represents the positive number and 1 represents the negative numbers. We'll see how to convert also. I'm sure you know it, but let's just have a quick recap of it. Let's just take a binary number, for example, given in the picture, that is 0110 and 1110. So first, to calculate the 2's complement, I need to take the 1's complement of it, right? So convert all the zeros to ones and ones to zeros, okay? So when I convert, I get the 1's complement. Now, to this 1's complement, if I add 1, that is at the units place, I need to add 1 and then find the result, which gives me the 2's complement. That is the negative representation of the original binary value. Here is an example for you on the right diagram. So binary representation of 5 is obviously 0101. You know it. You can use the 8421 code. So 2 power 0 is 1 and it is represented 1. So you need to multiply. And then 0 with 2 power 1 and 2 with 2 power 2. So that gives you 4 plus 1, that is 5. Now what you do, you need to take the 1's complement of it. That will give you 1010. Yes. Now all I wanted to do is add 1 to it. So you get 1011, which is the 2's complement. Now, why should this be minus 5? So the best way to answer the question is add it with the original value. Original value is 0101 and add it with 1010. Do the binary addition. You will get 0000 with one carry. You need to ignore the carry and take only the 4-bit representation, which is 0000. If you have a pen and paper in front of you, I would encourage you to do that so that you are verified. And I mean, you just get it verified in your minds once. So that is all about 2's complement. We will be building this also. Okay, so that is one more thing. And yes, a recap of combinational logic. Let us see what and all do we need to build the SAP1 computer. A half adder. We'll not be specifically using the half adder because when we use the circuit verse environment, there we already have adders at our ease, so we can at our disposal, so we can use those. But just so that we know how the adder works, here it is. The half adder will take two bits, that is A and B, and add it for you. It will give a sum, and in case there is a carry, it will give you a carry also. So you can see the truth table on your right hand side. That is 0, 0. It will give you sum 0 and carry 0, and similarly all other combinations which are possible with the two numbers, that is 0 and 1. You can see the sum, the column where you have sum, it is exactly the truth table of an XOR gate, right? Whenever there is odd number of ones, you get a 1, and if there are even number of ones, you get a 0. So that is XOR gate, and carry is nothing but if you see the only column of carry, it is nothing but the AND gate, right? All inputs are 0 unless and until both of them are 1. So that is how the carry works. So the same thing is built as a logic diagram. You can see that is what is inside an adder. And next thing is what we have, the full adder. Now, what is the advantage of full adder? Full adder can take a carry input from the previous addition and then use that to find the final adder, the final sum, and give you the carry along with it. Okay, let's just look at the diagram for that too. So here it is. If you build, if you draw the truth table for it, you can see all the possible combinations of A, B, C in is there. So when you see the value of sum and carry out, and you can use the K-map or any other simplification method, taking common, etc. Any method which you feel is comfortable for you, you will get this circuit diagram when you build it, right? When you simplify the expressions, either in minterm or maxterm, any formation you want. And you can find the same for the C out too. So this is the circuit which you will get it. This is a complete circuit for full adder. This is not the only way to do it. You can also build it using two half adders. That is completely your choice, but this is the circuit for the full adder. And similarly, as a black box, it is represented this way. We have three inputs, that is A, B, and C in, that is a carry from the previous addition, and then a sum and a carry out. So this was about full adder. We'll be using this a lot, and our computer basically does this. Okay. So yeah, using two half adders, that is how it is built. The sum of the first half adder is given as one of the inputs, and then carry in from the previous sum is given as the another input to the half adder, and finally the sum is calculated along with the carry. So can I get a quick yes or no if you were with me until this time? I haven't checked the chat from quite a long time. Okay, a quick yes or no if you. Okay, thank you. That's great. Okay. Thanks a lot. Thank you. Yeah. Okay. Now, we'll have a quick recap of multiplexers and demultiplexers. Now, what are multiplexers? Here is the quick diagram for you. Multiplexers is something which helps us choose. Okay, so we have a select line. This is the box which you can see, and in internal working is this. You can also build it using logic gates. It isn't much big of an issue. So the select line, whenever it is 0, it will choose the first input, and then if it is selected as 1, you'll get the second input. So it will just switch over between both of them depending on what value you want. Now, where will we be using this? This multiplexer we'll give it two inputs to it. One which has the addition logic and another which has subtraction logic, which we will build later on. So whenever I select 0, it will perform addition and then give the final result. And then whenever I select 1, I'll get to know that there is a negative number. I need to use the same circuit, but with the negative number so that it subtracts for me and gives the final addition. So that will be the application part of multiplexers, which we will use. And yeah, the truth table, etc. is given to you. You can build it on your own, or I would encourage you to write it also somewhere in case you haven't written in your digital design classes. Okay, so this is a truth table, and you can write the condensed truth table. And that's basically what I said a couple of seconds earlier. That is, if you select 0, you'll get the first input, and if you select 1, you get the second input. Moving on to the multiplexer, this is a 4:1 multiplexer. The other one was 2:1. Here, there are two select lines. Always it is 2 power n. Okay, the number of select lines, if you have 2, then 2 power n are the number of inputs. And yeah, if you select 0, 0 of C1 and C0, then you get the first input. 0, 1 gives you the second input. 1, 0 gives you the third input, and 1, 1 gives you the fourth input. it is relative. Here it is x0, x1, x2, and x3. You can have it x1, x2, x3, x4. It is completely up to you. Naming is your choice completely. So that's how the multiplexer works. A multiplexer is a shorthand for mux. Okay. So the next thing is demultiplexer. It works on a very similar principle, but the only thing is it has one input and many output. And many is nothing but in this case 2 power n, where n is the number of select lines. As you can see from the truth table, if I select 0, 0, I get the D naught output, and then that is 1, 0, 0, 0. If I select 0, 1, I get the second one, and similarly, so on and so forth. You can build again. I would encourage you to build this using logic gates again, so that you get a feel for it. So that's how the demultiplexer works. And yes, I forgot to tell you, in case you have any questions at any point of time, the chat box is always open. Please feel free to ask, and anyone of our team will surely address it. Okay. Next thing, tri-state logic. So the tri-state logic is usually in binary. Obviously, I said, there is 0 and 1. Then what is a third state? Uh, for that, to explain that, I'll just take a small example of a tri-state buffer, which you can see right in front of you. Tri-state logic includes an enable signal, which you see dropping from the top. That is EN signal. Now, from the truth table, you can see if I don't enable this buffer is something which holds the value until you want it in the further stages. It'll just hold it for you. Whatever is the input, it'll give you the same output. Okay, so that is a buffer. So that is used to transmit along, long distances, or you just need to hold it before you use it anywhere else. So that is why buffers are used. But if I give an enable signal, okay, if I don't enable and check the output of the buffer, you will get something called as high impedance. That is, you just don't know what it is. There is no output. So high Z. Z is for impedance. You would have seen that in your electrical engineering classes. Power will be, R by Z, etc. All those. So the same terminology Z is used here. That is high impedance. Okay, high Z. And yeah, if I enable it, you can see if I enable and I give input as 0, you get the output as 0. If I enable and if I give input as 1, you get output as 1. So it's as simple as that. The only difference between a normal buffer and a tri-state buffer is that I give an enable signal. Now comes the sequential part. Many students have a problem with this, but not to worry. We'll get the basics clear, and then we'll move on to actually building things using the D flip-flop. Yeah, so let's just look at the basics. Now, the D flip-flop can be either the positive edge trigger or the negative edge trigger. This will be available in the full explanation is available in our textbooks or anywhere else. All we care about is whatever we give input, we get it as output. And if we don't enable the flip-flop, we get the memory state. That is whatever was previously there in the flip-flop. The same thing is what is reflected in at the output. You can clearly see that is when D is 1 and clock is at the rising edge. The above the arrow pointing upwards means it is the rising edge. Okay, that is transition from 0 to 1. Okay, so at that instant, when you see the output, you will get the Q. Q is the desired output. That is same as the D. What you give as input. Similarly, 0 and 0. And if it is a negative edge triggered, at the falling edge of the clock is basically at periodic intervals 1 0 1 0. It will keep giving you so that things can happen at a synchronous pace. Okay, so yeah, the same thing. Output will be the same as input, but at the falling edge of the clock. So that is the truth table. And in case you want to build it using NAND gates, here is the circuit diagram for you. That's how a D flip-flop looks like. And yes, a small thing, you can see a NOT gate that is inverted there. You can also replace that with a NAND gate using the same input, just split it and give it to the NAND gate. You'll get the inverter. So in case you're building with only NAND gates, that is how you do it. Otherwise, if you have the flexibility of using other gates, you can use an inverter. But NAND is it is used far and wide because a single IC has the one which we use in our digital labs, etc. So that has 4 NAND gates, and in case you need to open different, use different gates, so it'll take more area of your circuit board, and then it's a waste of space. Instead, use the same one, and you can split the inputs and give it. Okay. So the next thing is D registers. We'll be building one of those now. Okay. So what are D registers? For our SAP computer, we'll be using a D register, which is either 4-bit or 8-bit. Here is a diagram for you. This is an example of PIPO, that is PIPO, parallel input and parallel output. You can clearly see I'm giving 4 inputs, PA, PB, PC, and PD. And similarly, 4 outputs are being taken, that is QA, QB, QC, and QD. That is parallelly, I'm giving 4 different inputs and I'm getting 4 different outputs. And it is synchronized with the clock, and we'll be building this. Now, I would like to ask you all to open your circuitous page, and let's shift there, and then we'll build the T register with some extra modifications. Are you all up for it? Have you all made your accounts? A reminder was sent, and in the email also we had sent it to ask you to make circuitous accounts. Yes, kindly open it. I'll share that tab. Okay. In your case, you might need to log in or sign up, and then you can launch the design. I have already named it as SAP1 workshop. You can keep similar names as per your comfortability, anything. Here you can see the circuit elements, a timing diagram, etc. So I'll just move all this below because we don't need that at present. Now, at the circuit elements, I would like to request you all to choose D flip-flop. So here you get a D flip-flop. That is one. And we need 4 of them. So I'll just copy and paste 4 of them. You can do the same. I'll just zoom it for you. Okay. So yeah, after this, I want you all to give inputs to it. Now, how do you give input? Again, just go to circuit elements and choose input. And there's an input box here. So just choose that. And yes, you can give, anyway, you just keep it anywhere. And then go to properties. You can name it as input, let's say IN. The name comes here. And in case you want to, you can label it anywhere you want. I'll not be, worrying much about the beautification process, but in case you need to, you can do it. Fine. Copy the same thing and paste again and again. That's 4 of them. And you can see D is the input everywhere. D, 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 D. So you can give it to those as input. All you have to do is just join the inputs. So that is done with input. Now I'll give a common clock signal. You can either search for the clock here or you can give an input here as a clock itself. There will be no difference. So I'll just name this as clock. I just need to pulse with it. That's it. Okay, so I'll name it clock. That's done. I'll pull here and then give it as clock to each one of them. You can do this too. That is the next thing. We have given the clock. Now you can see what are the other points are for. That is enable a preset and an asynchronous reset, and you have the output Q and Q bar. Okay. Now what we'll be doing is I'll take the outputs of each one of them, and you can take it this way. I will take a tri-state buffer, and before that I'll just give the enable signals also, input enable. I'll just take another input, that is anywhere you want to, just take one and then extend it until wherever you want, and then give it as enable signal. Okay, so that's enable signal. And I would encourage you to choose anything else. I mean, you can just explore with many options which are present here. You have input, output. You can use all different types of gates. You want decoders, multiplexers, etc. Sequential elements. Also, you can have all the flip flops ready. Okay, and miscellaneous. You'll have a few. Just when you have free time, do check these out. Okay, and yeah. Similarly, you can use a tri-state buffer. That is this one, tri-state. It has the name tri-state. You can have its orientation changed at this place. Label direction and direction. If I say up, it'll turn up. So that's how you do it. Kindly pay attention to the the points. This is enable. This is the output, and this is the input to it. So copy these. Okay, you can use Control C and Control V. They'll work. Then place 4 of them. Essentially, what we are building is a D register with tri-state buffer. Okay, so connect all the inputs. If interested, you can even beautify this whole process. Keep it symmetrical, etc. That's completely up to you. And choose an output also. You can take outputs from this. The thing which is missing is I need to enable these two. Okay, so I'll take another input and I'll name it as the output enable OEN. So that should help. And I have forgot to name this. That is IEN. That is input enable. Okay. So yeah, I can give. I'll just stretch this to, and then give it to all the output enables. That is one thing. And to see these outputs, I need to choose output. That is choose this. That is output. You can just copy paste this again. Move it a little further so you can see. You can also choose one and increase the bit width so that you can have all 4 of them in a single place. It is completely up to you. I'm just going the hard way so that you get to know and get a feel for the circuit bus environment. Okay, I'll just move this here. So that's how you do it. Yeah, we are done. And all that is missing is the asynchronous reset. So take another input, search for input, and you'll get it. Okay, it's a very friendly environment to work with, so it'll be easy. So you just stretch it everywhere, and then you can just drag it to asynchronous reset. Yeah, I'll just name this to this async, and we are done. If I enable the inputs and let's say I give 1010 as my input and I pulse the clock, you get the output as 1010, right? Now, let's say I disable the output, and then you can see high impedance state, and I'll enable it again. It gives the memory state. Okay, whatever, how many clocks I give, it'll remain the same. Why? Because I haven't changed my input. Now, if I disable the input and try to change this, change it to anything you want, and then pulse the clock, it will not change because I haven't enabled the input. The D flip flops are not active. Now I'll again enable this and change it to anything 1111, and then output is already enabled. I'll give the clock. Yeah, 1110. I'm sorry. Now if I do it, if I pulse the clock, it will change to 1 at the rising edge. In case you want negative edge trigger, you can put a NOT gate here and then an inverter and then do it. In case you are interested, you'll see the working of the flip top which is used here. Okay. I'll show you how to change the bit width, etc. That is a very good thing from circuit bus. That is, you actually don't need to do all of this. So go to circuit elements and then choose the flip flop. That will give you one here. Okay. Yeah. Zoom into this. Let's just see again the basics again. There is a D input as we saw in the presentation, and the Q will give the same output at the rising edge of the clock because zoom in. I mean, yeah, you can zoom and see this is a positive edge trigger D flip flop. And in case you want a negative edge trigger flip flop, you can add an inverter at this point and then do that also. I encourage you to try that out after the workshop when you're sitting at home at the night. You can just try it out all different permutations and combinations. Please do it. That will be a very good practice. And all the things you do on pen and paper, right? You can just do it here and verify and then do it in your assignments. So this is a very good environment to do that. Okay. So if I select properties for this D flip-flop, see you can see bit width here, okay? So you can increase that too. And then you'll have to give input according to the same thing, okay? If I keep 4 here, and let me take an input from here, choose input, and use the one. can keep it here. Okay. Then choose this and increase the bit width here too. Yeah. And then can connect it and then take an output. The output you can just keep it on this. Now it is giving a red thing because you have to increase to 4. Okay. Uh, yeah. So this was about the input and output, and I need to give an enable signal. Choose an input for that too. Enable is just 0 and 1, so you don't have to increase the bit width for that. I'm sorry. Again, I'll just change the orientation of this in case you want to see. Orientation, I'll make it upwards, so the dot goes up, and then I'll just join to the enable signal. You can name it enable. Again, just going over the basics. In case it was too fast for you when I was building this, you can see the individual what I was building here. You can do the same thing there too. Okay. Reset and asynchronous reset again. Take another input from here. You can just copy paste. It is completely your choice. Orientation, I'll make it up again and then join it to the input. And name this too as asynchronous reset. Anything. The clock. Yeah, input. Just join it with this. And yeah, this should be good. And in case you want to see the same working, I'll just move this. You can remove this and take a tri-state buffer and keep it here. Choose it and then increase the bit width here too. Okay. And then join it. The only thing missing here is the enable. So please don't forget this because without this, the buffer will not work. Choose another input and then give to this. So yeah, we are done with all of this. And just okay. Now you can clearly see. I'll give the input, let's say 1010, and this was the clock. I forgot to name this. A second. Clock. This table. So we are done. Okay, this is input and this is the output. So that is very evident. Now, let's say this is the input which I've given. I have not enabled the output. So first I'll do that. So any output is enabled. Now I have to enable the input again. And now if I pulse the clock, you get the same thing. Now just compare this and this. I made you do the dirty work because it is you need to know the working of each of them at a separate level so that that is how originally it is built. Now you can also try this out. You can take each D flip flop and build it using logic gates and still do it. That seem a very huge thing, but yes, it gives you an inner satisfaction because hey, you built it, right? So yeah, the simplest version which you can do is the same thing. Now just to compare, let's do the same
Skanda,
thing
one
here.
sec.
Yeah.
So there somebody has got an error. So I guess can you share your screen, Ankita? I guess we can show this to everyone also, so that they also don't end up making the same mistake.
I'll stop sharing. Give me a second.
Right. So so you can see the error down there called contention at tri-state. So what it means is that there are like multiple values fighting for precedence at the tri-state. Okay, or it even happens when you try to connect an input to an output. Like suppose there's like a road where vehicles are supposed to move like in only one direction, and then like you go in the other direction, there's going to be a contention, right? So I think that's what's happening here. So Ankita, if you can just select one of those outputs that you have given and check if it's an input or output in the properties. And then select, so it's an input, right? So see, so that's exactly the scenario that's happened now. So what you're essentially trying to do is trying to put two vehicles in the opposite direction on the same road. So that it won't allow you to do that. So what you have to do now is remove all of those and change them to outputs, so the traffic can flow out. That's right. So everyone also pay attention to this, because you might run into a situation like this later. Okay, so I think we can move on now. So
Yeah, okay then. Good evening, everyone. I'm Pratyusha R. So we'll be continuing with our session. So let me just present my screen. So remember when Ram Prakash started that we'll be building our own computer. So he mentioned three salient features of this computer, and one he mentioned was von Neumann architecture. I'm sure many would have heard across this in your computer architecture class. So just let me know in the chat box if you have heard about von Neumann, or you know what it is. If you know, you could just put it in a single line. Okay, Sneha says yes, that's good. You can even unmute and speak of whatever you know. It's rounding method. No, it's more of an architecture. You can take a clue of what is being presented right now. Okay, it's fine. I'll move on. So yeah, so it's an as the name suggests, it's an architecture. It's the type of how your blocks are being assembled. So you can see here, this is your CPU, Central Processing Unit, and these two arrow marks, they are the paths for your data to transfer from your memory unit to CPU. So in this architecture, what is happening is both the data part and the program part, both is stored in a single memory unit. So as you know, if you write a program in C and let's say C, and when it goes and gets stored in a memory unit, basically the program consists of two types of data, right? One is the data part, the data of the variables and stuff, and the programs. So let's say you write while loop, if loop. So that program also gets the commands also get stored, right? So in von Neumann architecture, both that commands and the data get stored in the same memory unit. So CPU at a single clock cycle, it can access either the data or the command. It cannot access both at the same time. So just to give you an heads up, there's another architecture called Howard architecture. In that, it has different memory units for both data and for the command one. Okay, so sorry, yeah. So the advantage of this architecture, it's pretty simple. As you can see, yeah, this is a very overview of the architecture, but the architecture will be simpler to understand. But in case of Howard, since you have to put so many buses from one block to another block, when you just look at the circuit, it might be a little hard to understand. So this is a quick recap. And SAP1 architecture, we'll be using this von Neumann architecture. So this is about it. Any doubts regarding this? Yeah, and also the speed will also be slow, because at a time you can access only the data or the command. So it's obviously going to be a little slow to load all the program content. Any doubts again in this? Okay, so moving on, another important part of our circuit is a bus. So again, let me know again in the chat box, do you know what this term bus means in computer architecture? Anyone? If you have heard about it, or yes, no. Okay, that's nice. So can you say what's a bus? Maybe put it in a single line. Yeah, okay, cool. Yeah, so as you guessed, probably, yeah, this is a bus. That's, yeah, maybe might be a lame joke. So on a funnier note, so it is a system in which the data gets transferred between the blocks, and it's also the path. It's also a way for your data to move between the blocks. So let's say you have a couple of registers and flip-flops. You need a way to communicate between those flip-flops to make a sensible logic, right? So what provides you that communication process? That is the bus. So, so if you see in this diagram, you can see there are many blocks, registers. You don't need to worry about this. Don't freak out seeing this diagram. It's fine. You will completely understand by the third day. So this is, you can see here, right, the W bus. This is the main bus, and the arrow suggests in which direction the data can move. So in the program counter, it's only a single direction. It can only give the output to the bus. So this is how it takes place. And one of the main reasons we have buses of this such organization, let's say your program counter wants to communicate with output register and RAM and so many other blocks. So if you exclusively make connections between all these blocks for that particular use case, your circuit, it's going to look super messy, and it will be hard to interpret it when you look at the architecture. So what we'll be doing is there'll be a main bus. You can, as you saw, using the control signals, you can control when the output, when the data should be on the bus and it should be not. So using that, you can decide what data should be in the bus. So this provides a very handful architecture to interpret our circuits. Yeah, so this was a brief overview. And let's see, there are mainly three types of buses. The main difference lies in what kind of data each buses carry. So let's go to the first one. It's the control bus. As you can see, carries control signals for controlling all the components. So as you saw, right, or even in the register, the input enable, output enable. So when you use a laptop, all those things get automatically set, right? When the output should be 0, when the input should be 1. So how does the how does your computer get to know when it should and when it should not? So the control unit takes care of that, and the buses which carry those kind of signals, they are known as the control bus. and it's unidirectional from CPU. It means ki it's the CPU, the control block which I just mentioned. It lies in the CPU. So from the CPU, it gets all its data from. Then the other part is the address bus. So if many of you, if you would have tried assembly language, you would have written load and you directly give the memory address, right? From this memory address, I need this data. So the buses which carry addresses of the memory of RAM or a second order memory, any such memory, they are known as the address bus. Yeah. And coming to the third part, it's the data bus. So yeah, let's say you've saved your program data. Let's say variable b is 8 in a memory, and that value 8, let's say it has to travel from block A to block B. So those kind of data which buses carry, they are known as the data bus. And only data bus is bidirectional because even CPU needs input, right? That when particular operations are being held, it needs input from its environment as well. So that data also the CPU gets from the data bus. So these are the main three types of buses. And yeah, as I mentioned, these are the three buses. This is a very overview and a possible way in which these three buses can be arranged. This could be a CPU as well. So as you can see, only data bus is bidirectional here, and you can see that for the output, all the information just goes in. So let's say your output could be an LED. So it just takes information and display. It doesn't give anything back, right? So these arrow marks, they present in which direction the data can flow. So now let's see in a register, in a circuit, how the data flows from one register to another register, and possibly what kind of mistakes we could do while building it. So I guess you can see this screen right now. So let's build another one. Let's say this is for first one. So yeah, everyone, if you had closed a tab or something, make sure you're on your circuit was page. So let's build this along, and it could also be a practice to get around with this circuit was environment. So let's get started. We'll build 3 registers here. So we'll take an D flip-flop here. Let's take 2, and then yeah. So this could be we'll make this an 8-bit register because as we mentioned before, this SAP computer deals with 8-bit architecture. So let's make this 8-bit just to get familiar with. So just press on this Control-C and Control-V. You are good to go with another register. Okay, this will make it 4-bit. I'll tell you why. Because CircuitVerse also supports nibbling. So we'll also see what's that. We'll give a clock first. Yeah, because usually sometimes what happens is in my digital design lab, I used to get to give clock and then wonder why I didn't get output. So I just always give the clock first. You can also enable or disable this clock here. So in the properties, you can see clock enable, right? So if you just switch this off, you can give this clock manually. So let's keep it manual for now. Let's make all the inputs. If you want to name these registers, you can. Let's call this A. Let's call this B, and yeah, let's call this C. So yeah, and input is just a single bit. As you noticed before, this could be of any number of bit register you are going to make, but the input it's going to be a single one. So okay, sorry, I'm just giving it a input here. This is so if you ever get confused what this dot represent, you can just hover around this. You see it says enable here. So I'll just make this up. Okay. Okay. Yeah. Yeah. Okay, so this is our enable signal, and this is our preset. So what this preset does is how your reset it sets to 0. Preset it sets your register to 1. Yeah, and it says here asynchronous reset, right? So does any of you know why does this say asynchronous reset, not just reset? So can you explain me that? If no, I'll just explain yes or no. Even if you guys are getting bored, you can just put it in the chat box or anything you didn't understand. Okay, so yeah, just give a quick overview maybe. It's called asynchronous because see, your sequential elements, they all depend on the either the rising edge or the level of the clock, right? But what this asynchronous means is even when the clock is not in the state of the rising or a falling edge, as soon as you set it to 0, the register immediately without any ideal delay, it gets set to 0. So if it was an synchronous reset, even if your input would have been 1, it will wait if it's a uh, uh, dependent clock. It will wait till your clock falls from 1 to 0 and then make the register 0. Yeah, so that might be handy for you guys to know. Just hold it. Yeah. So this is your input. Since it's an 8-bit register, the bit width also it needs to be 8. We put a properties and it's changed. Now it's correct. And the red line indicates that the state of this bus is unknown. And you would have guessed by now, light green is 1 and the dark one is 0. So let's give input to this one as well. So okay, why? Okay, cool. So what we can do is we'll put a tri-state as well to control when the output of the register should be on the bus and when it should be not. Because if this tri-state is not present, your bus simultaneously, both A and B register, they'll be putting their data on the bus. So that's what one of the reasons why you get contention tri-state error. So let's not make that. So okay. Let's move this here. Yeah. Okay, and before giving to that, usually your database, what it has is the database is usually divided into two buses. So if you say an 8-bit bus, usually in these architecture, this one bus, it will be for your program, the command. This bus will contain the command which is supposed to be executed, and this bus will contain the data. So let's use this, let's use a splitter to split this 8-bit into 4 bits and 4 bits. So when you go to miscellaneous and click on this splitter, it says here enter bandwidth. So enter bandwidth is the number of bits your splitter gets as its input. So here it's 8-bit, right? So let's say 8, and then it says enter bit width split. So so you have 8-bit here. How do you want this splitter to split? I want 4 bits and 4 bits, right? So I'll just give 4 and 4. I'll let's see. There it is. And yeah, as soon as you see something red, you might expect something is wrong. So and you need to make sure that everything is in 8 bits. So it's 1 here. Let's change it to 8. That's yeah, that's okay. Good to go. So let's connect to this and this. So let's put an output here to just keep a track of what output we are getting from this. Let's make this 4-bit and keep it on right. On this, yeah. Okay, so let's quickly do this for the other ones as well. So meanwhile, please try to build this with me. You'll get a clear-cut picture of the circuit environment. And you could also play around with this and see what kind of errors you might encounter into. So this is your input. Okay, never mind the space. Okay, so here let's just directly see the output here. You could put the tri-state and stuff. So we'll just use this for loading. And I'm input enable 1. It's important to build like small just circuits around this and get to know the environment. Okay.
Amrita wants to know how to use the splitter. Can you explain the splitter part again?
Sure. Yeah, sure. So yes, so you go to circuit elements and then you go to you can see the miscellaneous part, right? Just go there and click on the splitter. So enter bit width. What it means key. See, this is what is asking. So here at this point, how much is the length of the word? Sorry, how much is the length of the data you are passing on? So here, since it's an 8-bit register, it will be outputting 8-bit, right? So the input for the splitter is 8. So I'll enter 8 here. Okay. And now it's asking in how many bits do you want to split this 8-bit into? So here 8-bit what is 0 to 3 and 4:7 denotes is these 0 to 3, it represent these 4 LSB part, and 4:7 indicates these MSB parts. If I want, okay, so let's put here 4 space 4. Yeah, so this is how I get my splitter. So let's say your bit width is 4. Yeah, I mean, the input you are getting here is 4-bit, and then you want each bit out of this separately. So what you'll do is 1, 1, 1, and 1. So yeah, voila. So you see, you can give an suppose 4-bit input here, and you'll have your LSB here and MSB here in the same order. So you could play with this ratio and just see how it works for you. So I guess you understood, Amrita. Yeah, awesome then. Okay. Okay, so this is the input enable part. And yeah, if you want, you can give the reset as well. I mean, I'll not be using reset for now, so it's fine. Let me give the input to here as well. Okay. Yeah, this part I just omitted. If you want, you could put the output enable. That's it's your. Okay, guys. So this is the circuit we'll be playing with to understand how bus works more efficiently. You guys have built this circuit with me. How to get bus? Bus, you don't need to do much. Just just click on one of the points and you could just drag around and connect it. So just let's say if you want to give the reset here, just click on it and drag it through your mouse, and let's give an input here. So again, just click on it and you're done. That's it. Yeah.
Or see, to get a bus that looks like this directly, what you can do is, just select the output first. So the output, give it 4 bits, and then from the output you drag the wire down, straight down. Then you'll get a line that's connected to 4 bits, and then do the same for the other one also. You can do that as well.
Yeah. Anything. Yeah, that works, and it's. Yeah, like drawing buses in this, it's kind of intuitive. It's like when you go to Word Paint and you just keep clicking and dragging stuff. So yeah. Everyone with me till now, till the circuit, any other problem you guys faced? Okay, so let's assume you guys are busy building circuit to put in a chat box. Let's carry on. So let's say now from bus A to bus B, okay, first I'll load my input. For that, let me keep the output 0. So no data is on the bus. So that's why it's showing this red thing. That means it's unknown. It could be any value. Now, since it's 1 here, I'll load this data here. And okay. So when I clocked it, you can see the value E0. Basically, this is the hexadecimal representation. This 111 represents the E. So yeah, circuit words, people, they really built it very cool, because whatever data you put it here, so let's say you put 1 here and you can see this is 7. You could see it here. So now the data is loaded, and I want to turn this off, because see, now if I make any changes, the value of this register doesn't change at all. Now in this next cycle, let's put this 7 onto the bus. That makes it 1, and let's make this input enable also, yeah, it's already 1, so that whatever is there in the bus, this registers takes in it. So let's, yeah, so as you can see, the 7 has come here. So if my enable bit, see this enable bit, if it was 0, this data wouldn't have been loaded into my register. So what you have to do is make sure ki only one register is outputting its data on the bus, and only the required register input enable is set to 1. So that's how it is. Let's actually see what will happen if I try to put both these data register onto the bus. Let's make this one to load the. Okay, this is 88, and let's make this one. Yeah, you can see, right, contention at right state error. So as you can see, the value 000, and it's not any of the inputs we have given here. So since it's in simulation, it might pick up some pattern and give the output, but while if you do it in a physical circuit, you cannot make out what this data bus it's actually carrying. So that is how it is. So let's make this 0 and output this data on the bus. As you can see, this MSB bit is here, and the LSB bit it's in the second part. So any doubts till now? Any doubt? Maybe the register transferring thing, or the bus error thing. I could explain it again.
Like again, I would like to ask, how many of you have this circuit in front of you? Because if you're having trouble building this, please let us know, because this is the backbone of the rest of the computer. So everything is going to be like this. You can probably just continue from this for the rest of the things.
Yeah. Any part it might be very simple key. Why if I make this one it goes, and any doubt like how the splitter works? It's 4 bits taking as you can see. Splitter. Oh, okay, cool. Yeah. So again, you go to circuit elements, miscellaneous, and splitter. You click on this. Yeah. So wait, quick way. Enter bit. So you can see I have a splitter here, right? So what this is asking is, what is your width of the data you are giving into the input of the splitter? So it might be 4-bit or 8-bit. How many bits? So since this is an, as I mentioned here, 8-bit register, you can see it's taking 8-bit input, and according to the control signals, this register also gives out an 8-bit data, right? So your input for this is 8-bit. So let's click on 8, enter. And now you have 8 bits. You can split it into many ways. You can literally keep 1, 1, 1, and make sure keep the 8 bits. It's divided into all single bits. Let's do that. Okay, that's 4, 5, 6, 7, and 8. Yeah. So as you can see right now, let's just take this from here. So all these 8 bits, let's just put a output and just see. Yeah, as you can see, your first bit is 0. Your first bit was 0 right here. That's why you have a 0. Next, you should have a 1. Just quickly, let's just okay. No, I'm sorry. Like at this output, this is what it's carrying 1010. Wait. Uh, Let me just give a proper output and let's wait. Uh, yeah, since it was in contentious state at that time, I'm not really sure what its input was. So let's see. So as you can see, it's an 8-bit thing you have here. Let's make this. So now, according to this should be a 0, right? Let's check. Uh, yeah. Sorry. This is the LSB part. 0 is the LSB part. You can see it's 1 here. It's 1. If I change this to 0, you can see it becomes 0. So this is the LSB part. Let's go and check the MSB part here. You can see MSB is 0 right here. It's 0. Let's make this 1. You get 1 here. So you could make this splitter into 8-bit into 1-bit, or as I have done here, 8-bit into 4 bits. So what it does here is 0 to 3. So this upper nibble, it carries these 4 bits, and the lower nibble, it carries these 4, the later part, the MSB side wala bit. So I hope it's clear now, the splitter part. Even how to make a splitter as well. So let's say it's 6-bit you're getting, and you want it to be 3. You want it to split into 3 into 3, and then you give 3 and then 3. Yeah. So here you have it: 0, 1, 2, and 3, 4, 5. So yeah, that's it. That's how you make. So is it clear now how to use the splitter? Yeah, okay, that's awesome. So, any other doubt you want me to clear again, or play with this circuit and see how stuff actually work? So when I gave both 0, it was yeah, in this state you can see here that it has taken the first register. Yeah, since as I said, since this is a you can say key, okay, so whatever first register was given, that's it showing, like since it's in simulation, they have some kind of algorithm running behind, so takes it. But when you build a physical circuit out of it, it's going to be a complete chaos. I mean, it's just going to be XXX. Yeah. Let's make the 0, and you can see since it's 1 here, 1010, it's loaded here, and this is loaded here. As you can see, since I've not enabled the input here, the value of this register, it's not changed. So if I make this 1 and give the clock, you can see 8, it's loaded here. So these bits, they play a very important role in making this bus organization actually work. So usually what happens is when you, this might be a opcode in the sense, in assembly language, you might have written add. So add will also be a sequence of numbers in this. So this will carry those this bus will carry those kind of commands, and this will carry the address of the memory. So in sequential elements, you have a ROM here. Yeah. So yeah, sorry to break it to you. To get to know this, you have to attend our next session. So to get access of this address, this data bus, it will be carrying the address part. So if it was a 16-bit data bus, what would have happened is 8-bit for the command thingy, like technically called opcode, and the other 8-bit to access the address in the this memory part. Yeah. So this is how your data bus in SAP1 is organized. So this is one of the core concept, to understand. So in this presentation, as you saw before, you saw this 8-bit bus thingy, right? So technically, this is what this 8-bit, it's split into 4-bit and 4-bit. So that's what we just built, and we saw how with help of all these control bits, transfer takes place, and of what points we need to be careful while making the data transfer.
So again, everybody has built this circuit and got it to work. So have you tried out transfers like how Pratyusha showed? So if you have, please put a yes in the chat. Why did we split the bus? Right. So so we split the bus just as a convenience. Okay. So you see, what we could have done is taken a single 8-bit bus and then uh, take like split the bus into 4 and 4 later, like when we are taking data from the registers and stuff. But what if you want to do the reverse, right? Suppose we want to set only one half of the data, then you would have to split. So like she said, the 8 bits are divided in the each 4 bits have a specific meaning. So the first 4 bits are like one, the upper nibble, which is like the MSB part, represents the instruction. The other half represents the memory. So sometimes you would want to change only one of those. So that time you would have to have control like this, like half and half. So that's why we've split it into a groups of 4. All right. Okay. Any other questions? Actually, before I would like to give you a little fact. Okay. So when we discuss about tri-state logic, right? So there are the 3 states are what? 1, 0, and Z. So there's actually a specific meaning, like another the electrical meaning of each of these states. So let's say you have like a logic gate and you have a 0 in the input. So when you look at it like at a very deep low level, like say the transistor level, what it actually means is 0 means is current is flowing into that whatever pin. So you have an IC and you have there's a 0 at that pin, it means current is flowing into it. Okay. If it's a 1, it means current is flowing out of it. Simple as that. So the reason we need this high impedance Z state, so Z is, so current doesn't flow at all. So it's completely disconnected. So that is the meaning of the high impedance state. So if you don't have that high impedance state in the bus, unintentionally all the bits that are set to 0, current will be simply flowing into the circuit, which you don't want happening. So if you want to completely isolate something from a wire, you just use a tri-state. So when you disable it, nothing flows in between those two connections. So current doesn't flow in, current doesn't flow out. So that's just a quick fact about tri-states. Okay, bit width error. Do you mind sharing your screen? We can figure it out. Yeah. Okay. So so can you select that second flip-flop there? The bottom one. That's right. Click on it.
Is it this one?
Yeah, that one.
Huh.
Uh, is it 8 bits or 1? In the properties, when you click on that flip-flop,
Yes.
it's 1. So just change it to 8. That should fix it.
Okay. Thank you.
You're welcome. Also, another quick tip: when you're doing the splitting, so first it'll prompt you the number of bits, right? The bit width. So say you give 8, and then it'll ask you for the split. How do you want to split it? So you should give like let's say 1 1 1 1 1 if you want all separated out. So you should separate that with a space. So if I have 8 and I want to split into 4 and 4, so the second dialog box that shows up, you should give 4 space 4. So then it will split it into 2 groups of 4. If you want to split all of them into ones, you give 1 space 1 space 1 space 1 like 8 times. That will give you 1 1 1 1 1 1, all of them split out. So if you want, say, split into 3 and 5, for example, you give 3 space 5. So that's how the splitting works. So yeah, so that was basically what all we had to cover for today. So since we have all the fundamentals out of the way, from tomorrow we'll start actually building the computer. So please come tomorrow, then it'll be really exciting. So all these, so remember one more thing, save your circuits. So whatever you've built till now, do a Control S so that you don't lose any of your work. You can actually reuse quite a lot of the things you built today tomorrow.